You are surrounded by an invisible force field. You can touch it, you can hear it rattle against its frame in a storm, and you trust it to hold back freezing winds or the vacuum of the stratosphere. Yet, when you look at it, your eyes register absolutely nothing. This is the profound paradox of ordinary window panes. It is a solid object that behaves, to the human eye, as if it simply does not exist. To understand this illusion of nothingness, we must first look at what happens when light strikes a typical solid. When a photon, the fundamental particle of light, collides with a wooden door or a brick wall, it encounters an impenetrable fortress of tightly packed atoms. The electrons within these materials eagerly absorb the photon's energy, jumping to higher energy states. This absorption is what stops light dead in its tracks, casting a shadow and rendering the object completely opaque. But the material we look through every day breaks this fundamental rule of absorption, and it does so using one of the most opaque substances on Earth. It relies heavily on silicon dioxide, the primary chemical compound found in quartz and common beach sand. When you hold a handful of sand, it entirely blocks the sun, but subject that same sand to searing heat, pushing it past 1700 degrees Celsius, and the fundamental architecture of the material undergoes a radical transformation. As the molten silicon dioxide cools, it does not return to its original, orderly crystalline state. Instead, it cools so rapidly that the molecules are frozen in a state of chaotic suspension. They lack the time to align themselves into neat, repeating patterns. This creates an amorphous structure, a state of matter that is rigid like a solid, but possesses the randomized, disorganized molecular arrangement of a liquid. This chaotic architecture is the secret to its invisibility. In an amorphous solid, the electrons are bound tightly to their respective atoms. Unlike the electrons in a piece of metal, which roam freely, or the electrons in wood, which are easily excited, the electrons in this frozen liquid require a massive surge of energy to jump to a higher state. The energy required to make this jump is known in quantum mechanics as a band gap. And here is the cosmic coincidence that gives us clear windows. The photons of visible light simply do not carry enough energy to bridge this specific band gap. When visible light waves crash into the amorphous structure of silicon dioxide, the electrons cannot absorb them. Because the energy cannot be absorbed, the photons have no choice but to pass straight through the empty spaces between the atoms, emerging on the other side completely intact. The material is not universally transparent, however. If you were a bumblebee, capable of seeing in the ultraviolet spectrum, a window would look like a solid dark wall. Ultraviolet photons pack significantly more energy than visible light. When they strike the glass, they possess exactly enough power to bridge the band gap. The electrons absorb the ultraviolet energy, which is why you cannot get a sunburn while sitting behind a closed window. Harnessing this subatomic quirk was not a deliberate scientific endeavor, but a slow, accidental evolution of craftsmanship. The earliest recorded instances of ancient glassmaking date back over 4,000 years to Mesopotamia and Egypt. But these early artisans were not making clear windows. Their creations were opaque, heavily tinted by impurities like iron, resulting in dark greens and blues. They crafted decorative beads and small vessels, treating the material as a synthetic gemstone rather than a portal for light. It took millennia of trial and error for human ingenuity to clear the view. By the 1st century, Roman glassmakers began experimenting with chemical additives to neutralize the natural tints. They discovered that adding antimony or manganese dioxide to the molten sand acted as a chemical decolorizer. This innovation stripped away the cloudy impurities, yielding the first truly transparent panes. The ability to manufacture clarity fundamentally altered human architecture and our relationship with the natural environment. For the first time in history, a dwelling could be flooded with natural sunlight while remaining entirely sealed against the elements. The chaotic arrangement of molecules had been tamed, turning dark, drafty stone fortresses into illuminated sanctuaries. But the true power of this amorphous solid extended far beyond architectural illumination. Because light slows down slightly as it navigates the dense atomic obstacle course of the material, the light waves bend. This phenomenon, known as refraction, unlocked a new era of scientific discovery. By carefully shaping and polishing the transparent material, artisans realized they could manipulate the path of light itself, giving birth to lenses. The implications of that discovery still rippled through history. In the early 17th century, lenses were arranged into tubes, creating the first telescopes. When Galileo Galilei pointed his rudimentary optic tube toward the night sky, the transparent barrier did not just let light in, it brought the universe closer. He observed the craters of the moon and the moons of Jupiter, shattering the geocentric model of the cosmos and forever altering humanity's place in the universe. Simultaneously, the same material was curved to look downward, peeling back the invisible layers of our own world. Antony van Leeuwenhoek peered through tiny, meticulously crafted spheres of clear silicon dioxide to discover a bustling microscopic universe of bacteria and single-celled organisms. The frozen liquid had become a universal translator for the previously unseen extremes of scale. Without the unique subatomic band gap of this specific material, the scientific revolution would have been stalled in darkness. Biology, astronomy, and medicine were all propelled forward by a material that is defined by what it does not do. It does not interact with visible light, and in that passive refusal, it allowed the human eye to see the building blocks of life and the edge of the solar system. Today, our reliance on this transparent marvel has evolved from observation to communication. The same principles that allowed Galileo to see the stars now allow us to instantly transmit human knowledge across oceans. This is the domain of fiber optics, where strands of ultra-pure glass, no thicker than a human hair, form the central nervous system of the modern world. In fiber optics, we do not want light to pass straight through and escape. Instead, we want to trap it. By wrapping a core of highly pure silicon dioxide in a cladding with a slightly different refractive index, engineers create a phenomenon called total internal reflection. When lasers pulse digital information into one end of the fiber, the light ricochets off the internal walls, zigzagging down the microscopic corridor at immense speeds without ever leaking out. Every email, every streaming video, and every financial transaction traverses these transparent threads. The global internet is not a cloud. It is an immense, physical web of subterranean and transoceanic cables. We have taken the same material that once adorned the pharaohs and turned it into a conduit for the collective intelligence of the human species. It is a profound irony of the natural world. The clearest, most transparent substance we interact with daily is born from opaque dirt, forged in blinding heat, and defined by a chaotic, disorganized molecular structure. Yet it is precisely this atomic disorder that grants light its safe passage. From the earliest ancient fires to the digital pulses illuminating our modern age, the science behind this invisible barrier has done more than just let the light in. It has given us the clarity to truly see the world.